So now I'll go into the detailed working of this model. So before going into the details, I'll briefly review the background of automatic speech recognition, and as this is not the main focus here, and also due to my limited familiarity with this model, I will be rather brief with the background. So automatic speech recognition is the task of transcribing speech waveform into a text transcript. So the data set has n speech segments and n text and corresponding test transcripts. And speech is represented, usually speech is represented as a sequence of feature vector, where each feature vector is an m-dimensional continuous vector, such as the coefficients of Mel frequency capital coefficients. And text is also represented as a vector of the dimension of the vocabulary used. So the aim of this speech recognition is to build a probabilistic model to predict the transcription for a given speech audio. So ASR model themselves can be characterized into two types. So first is the hybrid models, and second is the end-to-end models. So hybrid models use three models to parameterize the joint probability distribution of speech and text. First is the acoustic model, which models the distribution of speech for a given phoneme sequence. Then we have a pronunciation model, which is a mapping from words to phonemes. And third is a language model, which models the distribution over text sequences. So with the three models, a hybrid system can compute the joint probability of speech and text as follows. It combines the model, or it combines the distribution of acoustic model and language model, and the acoustic model is conditioned on the pronunciation model. And you can see here that the acoustic model and the language model are not really dependent on each other. So language model is only dependent on the text data, and acoustic model is modeling the speech for a given phonemes, which is also not dependent on language model. So they can be learned separately from each other, and we can then later use them for inference. So for inference, we use the system of weighted finite state transducers, where we introduce a weighting parameter called alpha to weigh which acts as a trade-off between the accuracy of acoustic model and language model. And this alpha is determined on the cross-validation set based on this edit distance, which can be problem dependent. In this context, word error rate or phoneme error rate is used as the edit distance. And after determining alpha, inference can be done based on maximizing the likelihood. And unlike the hybrid models that I mentioned before, end-to-end models directly parameterize this conditional distribution of text given speech. So these are the examples of this model. I'll briefly go over CTC, as this is the most relevant to this work. So instead of maximizing the probability of derived forced alignment to hidden Markov model states, CTC directly parameterizes the distribution of alignment to text sequences. And so CTC predicts a distribution over text alphabet distribution given a speech sequence X, and the posterior probability of text sequence can therefore be defined in the following manner. And the likelihood can then become the likelihood can also be inferred in a direct manner. So while CTC is motivated by the end-to-end modeling of speech recognition, it can also fit in the hybrid framework of the hybrid model by replacing the acoustic model in the following way. And this is precisely how the wav2vec-U model works. It actually models an acoustic model in an end-to-end manner, and using the CTC framework, and then later use an independent language model to get the words. So this model also uses self-training. So in semi-supervised training, we have paired data and unpaired data. So self-training is one of the methods to utilize this unpaired data to improve the performance of speech recognition. So the idea here is to train the ASR model on paired data and then use the trained model to generate pseudo labels for the unpaired speech data, and then paired data and unpaired data along with the corresponding pseudo labels is further used to refine the ASR model. So as stated before, this work builds on the prior work of self-supervised, unsupervised and semi-supervised learning models for the task of speech recognition. They use self-training, they use a self-supervised model to extract speech representation. They use adversarial training for learning an unsupervised mapping of speech to phonemes, and their overall approach is inspired by some of the relevant unsupervised machine translation works. So now I'll go into the details of how this method works. This is the diagram of their ASR approach. So before processing, there is some pre-processing applied to the speech. An unsupervised voice activity detection model is used to remove silences from most of the datasets, but for one of the datasets, silence is part of the transcripts. So a silence token is part of the phoneme vocabulary that's used to represent phonemes. So this pre-processing is not done for that dataset. I'll mention about the datasets later as well. So wav2vec 2.0, the representations learned from wav2vec 2.0 seems to be the most important factor as to why this model does so well. So wav2vec 2.0 comprises of a CNN based feature encoder followed by quantization and then a transformer which is based on BERT. So this network is trained on these two losses. So the first loss is the first loss term trains the model to identify the true latent QT for each mask timestamp for a given distress. So as you can see in this diagram, for given this context and these Qs, this Q acts as the true QT and these belong to the set of Q tilde. And second loss term used here is the entropy term, which is the codebook divergent penalty to ensure that the model utilizes all the codebook entries. So this loss term should also be important as the BQVAs I think also suffer from this same issue of considerable number of codebook vectors not being utilized. So in this paper the authors use the publicly available so they use two wav2vec models. So in the training of this wav2vec unsupervised model, wav2vec 2.0, the representations learnt are frozen. So wav2vec 2.0 is not updated during the training of this model. So they used a pre-trained wav2vec 2.0 model. So they used two pre-trained models. So one of them is trained on this 53,000 hours of liberal light data, and the other is trained on this XLSR53, which is pre-trained on nearly 60,000 hours of speech audio in 53 languages. So wav2vec 2.0 architecture comprises of transformer with 24 blocks, and these are some of the other dimensions of the block. So then the question now arises is that out of the 24 blocks, which representation should be used? So they conduct a small experiment for that. So representations of different block were used to train different phoneme prediction network for 8 languages, and the average error is shown in these adjacent graphs on these two data sets. And based on these graphs, they saw that the 15th block representation resulted in the lowest test set phoneme error rate, and hence is used as a speech representation for the downstream task of speech recognition. So the question arises, why does the 15th block, or in general blocks 14 to 19, do well? So the authors say that the features from the later blocks are trained to directly predict the latent representations, so the which spans 25 milliseconds of speech audio, so which is much shorter than a typical duration of phoneme. And feature from earlier blocks capture mostly syntactic information, and there is not enough semantic information in that. So after obtaining the speech representation from wav2vec 2.0, they further segment the audio signals. Now, some prior works have shown that segmenting speech representations can help in ASR, as the right boundaries in the input representation makes it easier to predict the output sequence. So they collect all the speech recognition for the unlabeled speech data and perform k-means clustering to get 128 segments. And after segmentation, they compute PCA on all the speech-based representations, and to get a segment representation, they mean pool the PCA representation of all the vectors in that particular segment. Now, segment boundaries are noisy due to lack of supervision, and to deal with that, they mean pool adjacent segment representations as well, and that forms all the segment-based representation which is fed as input to the generator. Now, this is a visualization of how their clusters look. So this is, you can see that this GAN is the Viterbi decoding of their generator output, and it is compared with gold segmentation. So gold segmentation is essentially human leveled annotation, and at the bottom this is the corresponding spectrogram of the utterance corresponding to Jane may earn more. Although the input to their model is raw audio, they anyway show a spectrogram like that. So you can see that the k-means output is very granular here, and it underscores the importance of mean pooling adjacent boundary features for robustness. And what their generator is learning is the clusters learned by the generator is very close to the gold clusters, so which tells us their model is doing quite well. Now this is a clustering comparison, quantitative clustering comparison with respect to the gold segmentation with other methods. Now let me take a slight detour before I get to this table and explain why this table is very important. Like, although this table is not really a result of this paper, but is sort of an intermediate evaluation, but from my understanding this is a very important result in terms of giving an insight as to what exactly is happening in this model. So not for evaluation but for understanding purpose, I think this is an important result. So earlier I did mention that the authors leverage adversarial training to train a generator that maps speech features to phonemes. But there is another thing that I had not mentioned, is that they use a very simple generator architecture which has very low number of parameters. Now this begs the question as to, do they even need a generator at all, or why are they using a generator if it's such a simple architecture? They could have simply used the segments produced by k-means clustering and mapped them to the corresponding phonemes, right, which sounds simpler. So this table quantitatively answers the two questions that I just raised. Now if they had not used a generator at all, the granular k-means clustering output produces a very high precision but very low recall, and hence relatively low F1 score. And on the other hand, the generator output is much balanced in terms of precision, recall and F1 score. Therefore, what we can conclude from this is that the representation that we obtained after k-means clustering already had different phonemes segmented and embedded in different parts of that space, but the boundary between the segments was very noisy, and what the generator is essentially doing is that it takes this representation space and learns more robust decision boundaries which are smoother. As the major task of learning a representation space in which speech representation corresponding to different phonemes is already segmented, which by clustering the wav2vec 2.0 features, hence the task of the generator was to simply map the noisy decision boundaries to smoother decision boundaries. Therefore, they needed a generator they needed a generator to perform that task and to build a more smooth decision boundaries, but the generator needed to be simple enough so that it does not interfere with the representation embedding already done up to that point, and the generator can just focus on the boundaries. Now note that this interpretation is not present in the paper and is my understanding of what is happening in the model. So if you feel something incorrect or incomplete or anything with my understanding, do let me know. So I went through speech data pre-processing earlier. Text data is also pre-processed in a similar manner. So first the text data is phonemized, which means the words are broken into perceptually distinct units of sound called phonemes. Like cat is broken into plus k plus a plus t. And phonemization further converts the sequence of words y to a sequence of phonemes based on a phoneme inventory. So for one of the dataset, the phoneme transcriptions were already available, in which silence was also treated as a phoneme, but for other dataset, they used some already existing work to convert the text data into phonemes. So this was not part of their contribution. They already leveraged some other work to break text into phonemes. So silence token, and then after breaking the words into phonemes, they further inserted the silence tokens into the text. So why did they do that? Is that earlier I mentioned that speech data was pre-processed by removing the silences in between, but that's not always accurate, and many silences still remain in the speech. So to deal with that, generator is allowed to output silence phoneme tokens as well. But if the generator is allowed to do that, then we'll have a problem with that, as the phonemized unlabeled text does not have any SIL tokens. So to allow generator to output SIL tokens as well and still enable the training to work, they forcefully insert SIL tokens into the phonemized text data. So now the question is, where do you insert these SIL tokens? So they conduct experiment for that as well. So without inserting any SIL tokens, they get a phoneme error rate of 29, and then they insert SIL tokens at the beginning and end of all phonemized unlabeled sentences. This improved the accuracy, as the accuracy went from 29 to 25.8. Then they further experimented by randomly inserting SIL between words or group of phonemes corresponding to words, and they varied the rate of silence token insertion from 0 to 75%, and they saw that it works best for 25%, for which the phoneme error rate further reduced from 25 to 21. So they used the silence rate, so they used 25% as the rate of silence token insertion for all other experiments. So generator, as I mentioned earlier, it takes an input of the T segment representation as input and maps them to corresponding sequence of M phonemes. Now note that this T and M may be different. So why does that happen is that generator first predicts a distribution over the phoneme set for each segment representation. So for T segment representation, generator will output T phoneme distributions, and if it predicts the same phoneme for adjacent speech segments, then those are combined by taking an average of that. So therefore this M may be different from T. In fact, M will be less than equal to T, and the discriminator is a fairly standard one. So this is used as a fake data, this generator output, and for real data we use this phonemized text. So the overall loss function is as follows, and so the first two are the standard GAN loss, and GAN loss is further augmented with the gradient penalty loss and smoothness penalty loss. Smoothness penalty loss encourages the generator to output similar outputs for similar segments. So what I had explained earlier about smooth decision boundaries, and there's also this codebook diversion penalty, like that was also used in wav2vec 2.0, which encourages the generator to use as many to completely utilize the phoneme vocabulary. So the authors so there were still a few hyperparameters that need to be learned. The authors now propose a cross-validation metric for that purpose that does not require any labeled data. So for early stopping and to tune the coefficients of gradient penalty loss, smoothness loss, and phoneme diversity loss, they use this cross-validation metric. So this cross-validation metric consists of two parts. So first is the language model entropy, which is an indicator of how fluent that transcription is, and the other is the vocabulary usage, which makes sure to eliminate degenerate models which are outputting fluent but trivial transcription. So their overall metric looks as follows. So this HP minus log of UP. So UP is essentially the fraction of vocabulary of the phonemic vocabulary being used this point. So now that they have arrived at this metric which makes sense, so the next question is how to use this metric. So what they do is they generate these phonemic transcriptions for different training configurations and hyperparameter settings, and the model with the lowest value of this metric is denoted by p hat. Then they apply this constraint that any configuration which does not satisfy this constraint is eliminated. So the idea here is if UP cap is much lower as compared to UP, then they allow the model configuration which produced the transcriptions with higher entropy as compared to p hat. However, if UP hat is a lot higher than UP, that means the best performing model is using a much larger vocabulary, then other configurations will most likely not satisfy this constraint, and this factor of 1.2 permits slightly lower vocabulary usage for p as compared to p hat. Now after applying these constraints, they also consider the length of the transcriptions, and out of the remaining transcriptions they select the transcription with the lowest sum of phoneme entropy scores per utterance. So essentially they select the model configuration which produces phoneme sequences that score high under the language model but are not too long. So they further conduct this experiment to verify their unsupervised cross-validation metric. So they compare the performance of the model whose parameters are tuned using this metric to the model whose parameters are tuned using a labeled cross-validation dataset. And you can see from this table that there seems to be sufficiently high correlation between this unsupervised cross-validation metric and the performance of the model trained using a supervised cross-validation dataset. So which means that that this metric seems good enough to be used in its place. Now for decoding, they used so this is not essentially this is not part of their contribution. They use an already existing language model to convert the phonemes back to words. So they do multiple experiments in this. For some experiments they use a pre-trained transformer language model, and for other experiments they used a weighted finite state transducer with 4-gram language model, and they showed and they compare results of multiple approaches with that. So they further, after performing this unsupervised training of the GAN, they further refine the model with self-training. So for self-training they do 2 training iteration loops. So first they generate the pseudo labels of the training data with the GAN model that was trained earlier, and then they train a hidden Markov model on the pseudo labels. Then they further relabel the training data with the HMM and fine-tune the original wav2vec 2.0 model using the HMM pseudo labels with CTC loss. So HMM model uses phoneme as output while wav2vec 2.0 model uses letters, and both are decoded using the weighted finite state transducer decoder into words. So they use libdis speech dataset for this fine-tuning purpose, and this is the configuration of the wav2vec 2.0 that they used. So these are the datasets that they used, and so they conduct experiments for this timid dataset, LibreSpeech and LibreLite, multilingual LibreSpeech, alpha, and common voice. So common voice is a multilingual corpus that has multiple languages, and out of these 38 languages in that language corpus, they focus on the low resource languages of I'm not exactly sure about the pronunciation, but it's I think Kyrgyz, Tata, and Swahili as well. Okay, Swahili is from alpha dataset, and they also conduct experiments on these European languages of Dutch, French, German, Italian, Portuguese, Spanish, and Timet and LibreSpeech are English datasets. So their code is out, and they used FAIR-seq to implement their model, which is a sequence modeling toolkit based on PyTorch. And yeah, this is the generator generator specifications, and yeah, in only 90,000 parameters, so they use a very small model, which I explained earlier as well. And this is the discriminator specifications. And yeah, so they use, so their unsupervised, the GAN training does not take very long, it takes 12 hours, but yeah, wav2vec training and all that was done earlier, that would take a much longer time. And their loss coefficients are selected from certain range, so gradient penalty loss selected from 1.5 to 2, smoothness penalty decided from 0.5 to 0.75, and phonemic diversity loss was selected from 2 to 4. And to get the specific coefficient, they use that cross validation that I described earlier, and all the results are the weighted or the average of the models trained across different seed values. So this is the comparison of their model with supervised and semi-supervised method. So both supervised and semi-supervised method use 960 hours of label data in this table, and wav2vec-U uses 960 hours of unlabeled speech, and the underlying wav2vec 2.0, which was the feature extractor, was trained on Librelite LL60K dataset. So you can see that, so wav2vec-U is competitive with other supervised and semi-supervised models. Now this is a comparison with prior unsupervised work. So they compare with unsupervised work in two settings. So one is the matched setting, and the other is the unmatched setting. So in matched setting, unlabeled text data of the transcript is available, but like the speech text data is unpaired. Like, so the text has the transcriptions of the given speech dataset, but it is not paired with the corresponding text. And in unmatched settings, the unlabeled data does not contain speech transcriptions at all. So the unmatched setting is a much more realistic case. And in both these settings, the wav2vec-U significantly outperforms other other semi-supervised, other unsupervised approaches. Sorry. So this is the comparison of wav2vec-U on languages other than English, but still a significant amount of data is available for all these languages, as well as all these are European languages. And the performance is worse than supervised model, but it's still respectable maybe. So especially the more performance of the model with self-training is certainly respectable in comparison to the supervised learning based approach. So then this is the comparison on low resource languages. So for 1.8 hours of data or 9.2 hours of data. And so for this, representation of from XLSR 53 was used to so the wav2vec 2.0, which was used as a speech representation extractor, it was pre-trained on XLSR 53, and the GAN was just trained on this small amount of data, which also makes sense because the GAN is so their GAN is a very small, for both generator and discriminator are small networks, so it makes sense that they are able to generalize to small amount of data as well. So then this is an ablation experiment on the amount of data that they need. So LibreSpeech, which I stated earlier, comprises of 960 hours of data set, and in the text data set that was used along with it, it had like 31 million sentences. So first they try to reduce the number of they reduce the amount of audio data, and they found that 9.6 hours of speech data and 960 hours of speech data had roughly similar performance. And for sentences, they saw that 31 million sentences and 3000 sentences, so 3000 sentences data was sufficient to achieve good results, which was comparable to the performance of the model trained with 31 million sentences. So then they do more hyperparameter ablation. So they do this ablation with number of segments of k-means. So 64 gave this performance of 23.1, with 64 cluster, and 256 gave this performance and I think and in the final model they used 128 clusters, and similarly for PCA in the final model they used 512 clusters, and they show the experiments with 256 and 768 clusters as well. So in the discussion, the authors state two lines of future research. So one thing that they state that this work is based on phonemization of text data, and the model performance is very sensitive to the quality of phonemization, and phonemizers are not available for all the languages. So exploration of phonemization approaches that generalize across languages or unsupervised training with graphemic text units. So graphemic text unit is essentially the text unit corresponding to phonemes, has been stated as the future research. And also they use a very simple segmentation approach, like they use just k-means clustering. So they say that more complicated clustering approaches can also be tried in the future. So in summary, the authors presented a novel method for automatic speech recognition without any transcribed data. Their approach embeds and segments the speech audio with self-supervised learning representation from wav2vec 2.0. It then segments those representation and learns a mapping to phoneme with adversarial learning, and cross-validates hyperparameter choices as well as early stopping with an unsupervised metric that they proposed. And they outperform previous unsupervised approaches and are competitive with supervised learning approaches for European languages. They also validate their approaches for low resource languages. Okay, and that's it. Thank you so much.